Okay. So it's a great pleasure to have Angelica Jorba with us today and with the next 3 lectures. And well, for me, it's a great pleasure because I consider the group of Barcelona my second family, especially the University of Barcelona. And I miss it actually. But of course, Angel is a lot of, from the theoretical and numerical point of view, has a rich background, and I hope that we can all appreciate even whatever choice he made to present us. So please, Angel, the floor is yours. We are very happy to have you with us.
Okay, thank you for this warm welcome. So, so let me first give a few words about the kind of things I will explain. Finally, among my choices, I've chosen to be, let's say, a bit applied in the sense that I will present a few problems in celestial mechanics and astrodynamics on which invariant manifolds play the relevant role. So that will be the excuse to talk about invariant manifolds. I will talk about computing invariant manifolds, and I will talk about using them for understanding dynamics. So I will give a few theoretical references in case you want to study. So I also, at the end, I will give several references to enlarge what I'm saying. And well, if someone is interested in something, please ask here or contact me. I have also, I've prepared more material than I can use. So I don't plan, even if you see 34 slides, I don't plan to use all of them today. It was, for me, it was difficult when I started planning the course. I wanted to be more, I don't know, kind of encyclopedic, but I soon realized it was impossible because there's lots of things. And then I start focusing in concrete problems. And at the end, I thought that if, for a first course, it's also nice to see why they are so important, why we want them, when we, and the kind of use we do of them. Okay, so let's start. The first block, this today block, is about, I'll talk about center manifolds for Hamiltonian and non-Hamiltonian systems. Okay, the next, on next day, I will talk about the use of invariant manifolds to control a spacecraft in a space. That's another option. So I'll explain how they can be used for that. Then I will discuss about computing invariant manifolds for invariant tori. For some astrodynamics problems, and how we use them to understand dynamics, certain aspects of dynamics in the Earth-Moon system. So that's essentially what's the course about. Okay, so let's start then with center manifolds. Center manifolds is a kind of. Yeah. Is there any problem?
No. I think someone entered and then.
Okay. Okay, so the first, center manifolds are invariant manifolds, that are attached in principle to a fixed point. I'll discuss them attached to a fixed point. And this fixed point has some zero eigenvalues or with zero real part, okay? Usually people is, if you have studied bifurcation theory, you have seen center manifolds because, when a bifurcation takes place, when many bifurcations takes place, it happens that an eigenvalue is zero or has a zero real part. And then you use the center manifold to analyze the bifurcation. But that's not the kind of application I will do today. Okay, so the situation I will consider today is the one I mentioned here. So I have a region in phase space which is strongly hyperbolic. So this means that it's very unstable. So if you try to launch an orbit there, it goes away very fast, very quickly. And still in the region, you suspect you have periodic orbits or other kind of objects. So in principle, let me assume that this region has a fixed point, an equilibrium point, with a strong saddle that is responsible for the hyperbolicity of the region, and some center directions. The center directions give rise to bounded motions. So we want to study, visualize, compute, know which kind of bounding motions we have nearby. Okay, that's very interesting for space applications because it is very, I mean, those solutions, even unstable, they can be used for the design of a space mission. Okay, so very fast as an example, I will introduce the restricted three-body problem. That's very fast. I mean, I think everybody is familiar with it, but it's here. Let me choose Earth and Moon, 2-point masses that move in circular orbits around their common center of mass. So I use a reference frame that rotates with Earth and Moon so that the two masses are fixed on the x-axis. Taking suitable coordinates and units, the distance unit is the Earth-Moon distance, the time unit is such that the period is 2 pi, and the mass unit is the sum of masses equal to 1. With these units, the gravitational constant is also 1. And then you can write the Hamiltonian, which is that's very common. So this is a kinetic part. This is a Coriolis part because we are in a rotating frame, and that's the potential part. That's well, there's a reference in case you want to know more about it, how equations are derived. So here I will focus on this region, let's say L1 or maybe L2. This point is of center-center saddle type. So the saddle is very strong, either in L1 or L2. So it means that if you put, if you try to do a numerical simulation or something like here, everything goes away. Even, I mean, to find periodic orbits by simple shooting, it looks impossible. I mean, you have to do more sophisticated methods. And you want to know what kind of solutions are there. So we know that because of the centers, we have Lyapunov families of periodic orbits. That's a theoretical result that we can apply here. And I mean, if you know a bit of astrodynamics, it's also known that there's the halo orbits nearby. I will talk about them in a while. Okay. But we want to know what else is there. We want to describe, we want to produce a full description, okay? That is where the manifold enters. So, I mean, this problem is 3D, so 3 degrees of freedom for a Hamiltonian system. That means phase space has dimension 6. I mean, a phase space of dimension 6 is something hard to visualize. I mean, even if we have the energy, the Hamiltonian, which is conserved, is to be dimension 5, that's something hard to visualize. But it happens that as we don't care about the saddle, in fact, we want the saddle. What we want to do is to focus in everything which is not the saddle. That turns out to be a manifold, which is an invariant manifold, which is the center manifold. I mean, in this center manifold, the number of degrees of freedom is 2, so dimension will be 4. And because the Hamiltonian is preserved, the energy level is dimension 3. So that looks much better, okay? So this situation is common in many, many problems in dynamics. I'm using this as a first example. I will use a second example later, but that's very common in dynamics. I mean, in many, many dynamical problems, we have hyperbolic directions. Even in PDE's problem, we have an infinite number of hyperbolic directions that we don't care much. And a few, let's say neutral, central, whatever directions, that in principle, they should contain the periodic solutions, quasi-periodic solutions, or other kinds of bounded motion. And that's the one we want to study, okay? And for that reason, we focus on the center manifold that usually is of low dimension. And because of its low dimension, if you can reduce to it, if we can obtain this manifold, understand the dynamics on the manifold, we have a low dimensional system that we can visualize much, much more easily, okay? So that's the name of the game. So, well, I wrote some basic on Hamiltonian mechanics that I think I will skip. I don't think, I mean, depending on the audiences, everybody knows about Hamiltonian, but some other people's, I mean, depends on the background, they don't know anything. In fact, I mean, a Hamiltonian system is a very specific kind of differential equation in which the differential equation are written in this form, and H is a function called Hamiltonian. So I can pass you the slides in case you want to read them. So, it has several characteristics. I mean, Hamiltonian system has a strong structure, and this is something I will take advantage in a moment. So one of them is that the flow preserves the volume. That's a classical. So this forbids the existence of attractors. For instance, in a Hamiltonian system, you don't have attractors because of the volume preservation. So you have a symplectic form in phase space, which is given by this matrix. So that's the form. If I'm going too fast with this, please let me know. But I mean, I simply am also introducing the notation I will use. Another concept I will use is first integral. A first integral is a function that is constant on each orbit of the system. The energy is a typical first integral, but in mechanical systems, sometimes you have an angular momentum or some other quantity which is preserved. Okay, and that's a concept that we will use in a moment. Okay, another concept that we'll use is the Poisson bracket. The Poisson bracket is a bilinear operator that acts this way. So it's very simple. Is antisymmetric. That's also very easy. And first integral satisfy this equation. If H is a Hamiltonian, F is a first integral if the Poisson bracket between H and F vanishes identically. The proof is is straightforward. It's one line. It's written down there. So Poisson brackets have several identities. That's the Jacobi one. Another definition: two real functions are said to be in involution if the Poisson bracket is 0. Another one is functions are said to be independent in some open domain if the gradients at each point are really independent. That's another classical concept. Okay, I think I repeated that one. Okay, well, the first integral is Poisson 0. That's a Dirichlet theorem. Well, but in fact, I don't need it. So let me. The last block of tools I need is canonical transformations, because I want to do changes of variables. Okay, changes of variables is called a symplectic or canonical transformation if it's Jacobian at any point in a symplectic matrix. That is, that identity is satisfied for any Z0. Okay, J is the matrix, that matrix. Okay, this is the one that defines the symplectic form. Okay, so these transformations are very important because symplectic transformations preserve the Hamiltonian form. This means that if I have a symplectic transformation, I can apply it on the Hamiltonian or on the differential equations, and I get the same result. It is the same thing. So, and that's very interesting, and this is one of the places when we take advantage of the Hamiltonian structure. So in order to make changes of variables for the differential equations, instead of working on differential equations, which means working with several equations, it's a full set of equations, we will work with a single function, which is the Hamiltonian, and we will do the changes of variables on that function. Okay. At the end, I will discuss what happens for non-Hamiltonian systems. Okay, that leave that for the end. But first, I will use the system that has the Hamiltonian structure. Okay. Well, finally, is a reference that, I mean, I was doubting about writing this theorem, but I mean, is the Arnold Theorem, that it means that if you have a sufficient number of first integral, your system is can be solved, is integral. I mean, so in principle, in the case that the level sets of the first integrals are compact and connected, then the phase space is foliated by invariant Tori. Okay, we will use some of that also in the. So I'm giving, this is the Arnold, the Dynamical Systems 3 book. So at the end, the reference is at the end. Okay. So another concept related to that is the action angle variables. They appear here, in fact, in the Arnold Theorem. So the action angle variables is the good set of coordinates for an integrable Hamiltonian. I mean, every integral Hamiltonian, you can transform it into action angle variables, and then the Hamiltonian only depends on the action, not on the angles, such that the equations of motions become integrable. Okay, so I'm going very fast. I mean, I know this topic could be tough by itself, but I'm going fast because that's not my goal. I only want the definitions, but if someone feels lost, please, you can ask me at the end or whatever. Okay, so let me. Okay, usually, I mean, in many cases, this derivative, so that one here, okay, that's called the frequency map, because to every action, you have the frequencies of the motion. So if this is diffeomorphic, which happens in many situations, not always, but in many situations, then sometimes allows you to identify a torus by its frequencies. It is because of the diffeomorphism between the actions and the frequencies. So, and then if the frequencies are resonant, then we have, I mean, the torus is not, let's say, maximal. The torus is filled by lower dimensional tori. And if all the frequencies are independent over the rationals, so if this product is always different from zero, then all the orbits are dense on the torus. That's also when alone, I think. Okay, so let me go straight. So, well, that I doubt it. I mean, that's very easy. I mean, for an harmonic oscillator, so you can do these things very, very easily. So that's the harmonic oscillator, that's the Hamiltonian, that's a transformation. I mean, if you want to transform to action angle, I mean, if you try something like polars, that's wrong because this is not canonical. So you can do that change, but not on the Hamiltonian. You have to do it on the differential equation. But if you check this transformation, this is canonical. So you can simply apply this to the Hamiltonian, to this. So you get that the Hamiltonian only depends on the actions, and then the system is solved in this set of coordinates. You can do that in more complicated Hamiltonians, but I chose that for a fast example. Well, so canonical transformations are very interesting because they allow us to make transformations directly in the Hamiltonian. So that's the point. I mean, I do this transformation on this, and I don't care about the equations. I simply work on the Hamiltonian. But the point is that to ask to a transformation to be canonical is something in principle hard. I mean, it's very hard to impose to a transformation, which has to be a one-to-one smooth transformation, to satisfy this at every point. This is a PDE. I mean, I mean, solving this is not feasible, okay? But luckily, there are some tricks to produce canonical transformation. So I'll focus on one of the tricks. There are many. I'll focus on one. So first is based on this property. So if I have a Hamiltonian system, and this is the flow, time t, at some time, then this is a canonical transformation. So the flow of any Hamiltonian system defines a canonical transformation. Okay, well, the second property, which is very, very interesting, is that one. So if G is a Hamiltonian system, and this is a solution of G, so this is an orbit of Hamiltonian G, then for any smooth function, okay, so warning, for me, here everything is smooth, which means, let's say, analytic. Okay, I won't discuss with finite differentiability, or so I will assume I can take any derivatives as I want. I mean, and that happens in celestial mechanics usually. Okay, so let's see the property. So I have an orbit of G. F is any smooth function. Then the derivative of F on a point of the orbit is also equal to this Poisson bracket in the same point of the orbit. The proof is one line. Is simply doing the math. Okay. Well, so why is this property interesting for this theorem? I mean, this property is using this theorem, which is, I mean, I call it theorem because it's important, but in fact is a corollary of what I've just said. Okay. So let H assume it's a Hamiltonian, and then we have a second Hamiltonian G, and this is the flow of the second Hamiltonian G. Okay, so this is a canonical transformation, so I can transform my initial Hamiltonian. I can do a changes of variables using this flow. That's a transformed. Then I have an expression for this transformed Hamiltonian, which is this. Okay, I will discuss this expression in a moment, but this is, I mean, at first sight, so this is a spectacular. And let me call your attention why I call it a spectacular. Okay, because H is a Hamiltonian you have, assume I give you G. G is another one. Assume I give you 1. Then, of course, to do a transformation in principle, you would need to know the flow of that one, which means solve it, which means to solve it, to find the flow at some time for all x, y in a domain as initial conditions. So that's a strong requirement. But I'm telling you that this composition can be expanded such that this flow is not there. So this is a Poisson bracket between H and G. This is derivatives and products. Again, derivatives and products, derivatives and products. Okay, so I can transform using the flow of a Hamiltonian without knowing the flow of the Hamiltonian. That's fantastic. Okay, that's a very powerful. Of course, this is an expansion. I mean, there's always a price to pay in mathematics. I mean, nothing comes for free. I mean, this is a power expansion. And well, this is true when the expansion converges. Okay, the proof is very easy. So you take this, you apply Taylor at T0, and for the derivatives involved, you use this formula. And that's it. There's nothing more than that. Okay. Well, okay. So let's try to use this. This expression is very suitable to do computations because it's derivatives and products. And the second comment, okay, is here, but let me go back, is that if this Hamiltonian is already a power expansion, I mean, this is not a huge price because this is already an expansion. So assume H, I expanded in Taylor series. And G is also expanded. I mean, that's not hard because we will choose G. Okay, so we can choose it. Then this is the Poisson bracket of power series. I mean, so it means derivatives of power series or polynomials, if you truncate the series, which is easy to take derivatives of polynomials, and products of polynomials, which is also easy. So this is going to be easier than it looks. Okay. So that's the second comment. All the operations are very simple if we work with some kind of expansions. Okay, so I've only mentioned power, but if they were Fourier, that's the same concept. Then there's a property that I will use. I mean, I don't need to enter. So in principle, if I have two homogeneous polynomials, f and g, the Poisson bracket is again an homogeneous polynomial, but the degree is the sum of degree minus 2. That's the. We will use that in a moment. Okay. Okay. So that's the machinery. Okay. So now let's try to use all this to do something. Okay. To study the problem I mentioned before, to compute the invariant method. Well, I mean, of course, everything here was infinite series, but we will truncate, so we will work with high order truncations. Which will be enough. It is also possible to derive estimates on the size of the remainder, and we can derive bounds. I mean, we can even do it rigorously, I mean, in a theorem-like form, okay? But I won't do that, but that's possible. And so let's focus, okay? So assume we have an equilibrium point. You can think of L1 or L2. It's a point center, south. The saddle, I mean, we don't want it, we want to remove it. So we want to do changes of variables such that the two centers are decoupled from the saddle. Yeah, so if you see in my hands, I mean, I want to do a changes of variables such that the two centers, which is the center manifold, becomes as the horizontal plane, the saddle becomes the vertical, and the center plane is invariant because they are decoupled. Okay, so I want to compute an invariant manifold that contains the two centers. And that manifold contains all, let's say, bounded solutions. They have to be there. Because on the other, I mean, outside you have the hyperbolic behavior, so you are sent away by the instability. Okay, So, well, I've put in some references about center manifolds in case someone wants to read more about them. So they are, in fact, there are 3 books, well, almost books. So, or survey articles, and very classical. So they are at the end in the slides. Okay, so, well, let's do it. That's quite fast now. So there's a Hamiltonian, for instance, the restricted three-body problem. I expand in L1 or L2. As L1 is equilibrium point, the expansion starts at degree 2. Okay, that's because in an equilibrium point, the function, the vector field vanishes. Okay, so it means degree 1 cannot be there. So that's degree by degree. And the second degree has this form. I'm using complex coordinates because everything is clear and even the computations are simple. So this is the saddle. That's the hyperbolic eigenvalue. Lambda is a real value. And this is the 2 centers. Okay. These omega 2, omega 3 are purely imaginary. So I should have written they are purely imaginary. So they have no real part, 0 real part. Okay. Well, now let's see how we decoupled. So in this degree, they're already decoupled. Okay, if we truncate at second degree, that's too rough, but I mean, if we truncate at second degree, which is equivalent to linearizing, it is the same thing as linearizing. Here we have the hyperbolic part and the 2 elliptic parts decoupled. I mean, I can set Q1, P1 to 0 and focus only on that part. I mean, this is, let's say, useless because it's only a second degree approximation, so that's not enough. But well, let's try to do the same for H3. So how can I do that? Well, I will do a changes of variables by a Hamiltonian G3 that I will choose. Okay, let me choose it as a polynomial of degree 3. Why degree 3? In a moment, you'll see what happens with degree 3. And what I have to do is, in fact, to determine the coefficients of these monomials of the polynomial of degree 3. Okay, if I do this, so now I'm not writing the calculations, but that's very simple. So now I'm doing this. So this means I'm using this formula with T1. I use T equal to 1. Okay, so there's a reason for using T1, but I won't stop margin it. But you can think that if for T1 converges, we are all happy, right? But there's another reason. I mean, T1 always works for a reason that I won't enter. You know. And then you separate degrees. Okay, so essentially the degree 2 here is the degree 2 of that part. Because this has degree 3. Remember, this has degree 3, and I have this property that the degree of the Poisson bracket is the sum minus 2. So if I have terms of degree here higher than 2, when they have the Poisson bracket with G3, they get degree higher than even 3. Okay, so degree 2 only comes from here. Here everything gets degree higher than 2. Degree 3 comes from here, degree 3, and when you combine degree 2 here with 3 here, because 2 plus 3 minus 2 is 3, and nothing else. So that's essentially you do this counting, and you get this. Okay, but that's very good because I can tell how a Hamiltonian of degree 3, G3, transforms H3. So H3 is transformed by this. So, and this is the formula I will use to determine which G3 I want, such that H3 is, let's say, uncoupled. Yeah. Okay, so let's look at this equation. So now is linear algebra, is manipulating expressions. So G3, that's an expression for G3. This I don't know. That is what I'm looking for. H3 I know. That's the power expansion of my Hamiltonian. So those I know. And this is the result. Okay, let me call it this. Okay, so if I do this calculation, this is taking derivatives and multiplying, that's what you get. Yeah. And okay, yeah. Now I have to decide what I want to do. So you have to think that to every H3, to every monomial, for every monomial, so when you apply a transformation, any coefficients will be combined, will be added. I mean, I will add this and this to obtain the result. Yeah. So here I could even choose G and to kill all the monomials of degree 3. That would be possible. If I choose G, okay, as minus HK divided by this, when I do this operation, G3 gets cancelled completely. I could do it. Yeah, because, well, you have to think that. Huh? I mean, that's a transformation you are doing. G3, you will choose it according to do what you want. So when you do this transformation, you add this guy to this guy. And that G here, you can choose it. So you can choose it so that when you do this, the summation, everything gets cancelled. You could make H hat 3 to vanish. Okay? We would do that if we are doing normal forms. I mean, in a normal form computation, that's what we would do. But this is not what we want. There's a reason for that. Okay? So, I mean, the domain of the convergence of this expansion depends on the transformation we do. So the more far from identity the transformation is, the domain becomes smaller and smaller, and I don't like it. I want the result to be valid in a huge domain, as big as possible. So because of that, I choose to alter this H3. I want to alter it as little as possible. Okay, so how I do that? Well, so the idea is the following. So first, at first sight, it's hard to see. So let me believe me. So in principle, I will kill the monomials such that the first component of the first exponent of Q is different for the first exponent of P. Why is that? Well, once I have defined that, so let me simply write it. That's the G3 that makes that. S3 is the set of indices in which the first component is different from the of Q is different from the first component of P. But the point is that once I have transformed H3, let me look at here. Here is the part I have arranged. H3 has this form. So it depends on the product, and it does not depend on each variable separately. Okay, and what's the advantage of that? The advantage of that is the following. So let me jump for a moment. Is that it's very easy to check that this is a first integral. So in fact, my Hamiltonian depends on this product and the other variables. This is first integral. Then if I set it to 0, remember this is the hyperbolic behavior, so I'm skipping. I obtain a Hamiltonian that does not depend on the hyperbolic variables, only of the central variables. Yeah, that's the idea. So what we are doing, let me use another word. So usually, I mean, in all the computations of manifolds I will do, that's the only one that's different. In all the rest I will do, I will really compute the manifold. So we will have the manifold. Here, what I'm doing is to do transformation such that the manifold becomes one of the coordinate planes. Okay? So usually we will go to look for the manifold, but here we do the reverse. We bring the manifold to one coordinate plane. So I'm doing transformations and I'm flattening completely the manifold. That's what I'm doing. Okay. So this is, let's say, it's a standard procedure when you work with linear systems. In linear systems, when you work with matrices, you usually take good coordinates such that every kind of behavior is a different plane. So you diagonalize, or you make blocks 2 times 2. You want to enter the complexes. Here we are doing the same thing, non linearly, up to high order, and we use the Hamiltonian structure to do it on the Hamiltonian. That's what we do. That's the concept. Okay, and I think that's the important part. All the rest is doing the calculations, doing the math, which is not that difficult. If this is the first time you see this, I understand you may be overwhelmed by so many formulas and so on. But believe me, there's nothing else than manipulating polynomials, derivatives, multiplications, blah, blah. Okay, that's the idea of. Okay, so let's see what happens. Well, first, that's a comment. I will repeat it later. This process has no small divisors, which is very nice. Maybe you have never heard of that, but if you have worked with K in theory or quasi-periodic solutions, there's something called small divisors that is responsible for the lack of convergence of many expansions. So here we don't have small divisors. So the behavior is very, very good. So I don't claim this is convergence, okay, but it looks like it's convergent. I will go back to this point in a moment. So I can also compute the changes of variables. So applying the same transformation, not on the Hamiltonian, but on the coordinates, I compute the change of variables. I won't enter into that, but it's simply, I would repeat the same argument. So that's a numerical example. So this is for the L1 point in the Earth-Moon system. Well, that's the mass parameter for the Earth-Moon system. Sorry, Earth-Sun. No, that's Earth-Sun. So that moon here is wrong. This is Sun. I'll correct the slide before giving them to you. So this is Sun. Okay, we have to do the computation up to degree 32, which is very high. Here I'm showing the result only up to degree 5. So that's the monomials, and that's the coefficient. That's what you get. The program is a C program that I have it in the public domain. It's in my web page, so you can download it, or you have any problem, you can write me. At the end, I'll give you. I have a reference explaining how it works. Okay. So, well, we can compute the radius of convergence because this is a power series. We can do the quotient criterion, root criterion, blah blah. As we have the changes of coordinates, a nice trick to see how how this behaves is to compare numerical integration on the center manifold, which is a power expansion. You can integrate with any numerical integrator, sending this numerical integration to the initial Hamiltonian and integrating there again and comparing. With this, you get an idea of how far you can go with this simulation. Okay, well, now it comes the good part. So we want the center manifold, we want this invariant manifold to understand the dynamics. That was the goal. So how we do that? Well, now we have 2 degrees of freedom. Okay, we have 3. That's the residual three-body problem. We have 3 degrees of freedom. The L1 point was center saddle. We have just removed the saddle, so we have only the 2 centers. So it's 2 degrees of freedom. So the phase space is 4-dimensional. So let me take a Poincare section. This corresponds, to visualize, to use Z0 in the initial coordinates of the residual three-body problem. It's 3D. And well, this is still a Hamiltonian system. So I can fix the energy level. So it's 2D. So I can plot. Okay. That's, that kind of thing is one of the reasons why we use invariant manifolds, because we decrease instead of working on the full phase space, we work on a sub-manifold of the phase space with lower dimensions, where everything we are interested in happens, and we focus on that. Okay, and this is because the dimension is lower, you can do things easily. Well, to obtain a picture of the phase space, we can simply, well, do a typical plot. I mean, we iterate orbits and we plot the orbits, varying the energy level. Yeah. So let me go to the result. So I put references for in case you want to have more material on this. So that's for a low energy. So what's this? So let me explain what's this. So here in the middle, I mean, everybody that has done a little bit of dynamics guesses a fixed point. Okay, there's a fixed point, elliptic fixed point in the middle. Okay. Okay, so you have to visualize this section as you are on Earth looking at the sun. L1 is in between. And the plane in your screen is in fact the horizontal plane in your eyes, that way. So this fixed point in the middle is a periodic orbit that goes up and down. So in this section, you see this periodic orbit as a fixed point. Okay. This periodic orbit is surrounded by invariant tori. And if we keep moving out, we arrive to this. This is the boundary of the section. And this is another periodic orbit, which is a periodic orbit in the plane, in your visual plane. Okay. And this is some kind of a sphere because I'm fixing the energy level. Okay, because the energy level is fixed to this value. So I have this vertical oscillation, the planar oscillation, and the quasi-periodic motions in between. Yeah. So, and then, I mean, I can plot that very, very easily because here the hyperbolic behavior is not present. Okay. So, I mean, the hyperbolic part was huge. I have an eigenvalue with a real part of order 1000. So if I had the hyperbolic part, I could not integrate and see this, no way. But because I've reduced the Hamiltonian to the center manifold, and I only work inside the manifold, I don't see the hyperbolic behavior. So I can do this. The another good thing is that here I'm looking at everything that is in the center directions. I don't need to guess if there's kind of periodic orbit or another kind or what kind of quasi-periodic orbit, because I see all of them. But if I increase the energy level, we see that something happens on the two sides. Let me increase, before discussing what happens, let me increase more energy level. Let me increase more. Okay, so here you can guess. So let me make the discussion here. Here we have 3 periodic orbits. This one is the one I mentioned at the beginning, the vertical oscillation. In fact, is the Lyapunov. This orbit becomes the Lyapunov family, the vertical direction. And these in the sides are called halo orbits. So these halo orbits, if you are at Earth looking at the sun, you see them moving around the solar disk, okay? Because they go from here to here and back. And there are 2 of them. Okay, one, they have a symmetry, okay? One goes, crosses and comes back, and the other one starts here, crosses and comes back. There are 2 of them. Okay, and that's all. Here we have everything visible. I mean, so in this way we can catalog all possible orbits. So, and this is one of the utilities of the invariant manifolds, right? So, I mean, in phase space, which is 6 dimensions, I'm able to focus in only 4, which is where the interesting motion for me takes place. So I focus on that 4. And there, because it's 4 and not 6, I can do plots and see everything. Okay. Okay. Here I have a second example, which I'll go very fast. It's a second situation. It's a solar sail near an asteroid. So let me go very, very easy. So 5 minutes, I'll use it. So this is an asteroid. This is the solar radiation pressure, that's solar wind. And this is a solar sail. A solar sail is a small spacecraft with a big reflecting surface, such that the reflection of the light on this surface, the sail, gives us a small push. The push is very, very small, but it acts for all time and is free. So that's an option for some missions. Okay, so I won't enter in solar sails, but this can be written in a kind of model. So here we will use the Hill model. In the Hill model, Sun is very, very far away. So that's the asteroid. We are close to the asteroid. We feel the gravity of the asteroid. And that's the augmented world. We feel the solar radiation pressure. So this push of solar radiation pressure is very, very low. It's very, very little. But so is the gravity of the asteroid. The gravity of the asteroid is also very, very small. So they compete, in fact. And that gives to a lot of interesting dynamics. Okay? And we have the same kind of situation. So we have an hyperbolic directions and center directions. So to visualize the kind of possible directions, we apply the same machinery. Yes, I'm finishing. So that's the differential equations. That's how a solar sail works. I will skip it. And that's the Hamiltonian.
Feel free to go a little bit. It doesn't need to rush.
Sorry?
You don't need to rush. You take your
Well,
time.
I like to keep the time, but I mean, no, I was not planning to finish everything. But simply, this first part, this is the Hamiltonian of the Hills problem. And that's the force due to the solar sail, to the solar radiation pressure. Okay, so that's 3 parameters. Then we can apply same machinery. So I won't repeat. So blah, blah, that's the same discussion as before. And we can, well, that's second degree. We apply the same machinery, blah, blah, Poincare section, same thing. And now, well, for some values of the parameters, we see essentially the same we see before. But for some others, we start seeing different things. So in fact, these and these are the same, but the section is different. We are using different sections. I will discuss. I mean, this is in fact, here there's a pitchfork bifurcation takes place that in these coordinates is not very well seen, but in this one is seen much better, the pitchfork. And this is, well, other kind of situations, it happens. So here we have an orbit, another in the middle, these 2. Here I have many. So the situation is much richer. Okay, I put the plots because I had them. So it costs nothing to add them, but I don't plan to discuss each plot. But here, because of the solar radiation pressure competes with the gravity of the asteroid, you have lots of things happening. And this is very difficult to discuss if you don't reduce to the center manifold, because all the everything becomes more and more difficult. Okay, that's another example of things. That's about the divergence or the conversion of the expansions. So that's the estimation of the inverse of the radius of convergence of the series. That's the root criterion. And it behaves like a logarithm. So it means this process, when the degree goes to infinity, in fact diverges, but very, very mild. But as we don't reach to infinity, we truncate, so we don't have this problem. And the last part, and that's the end, I mean, well, if the system is not Hamiltonian, we can still do it. But then we have to work on the differential equations, not on the Hamiltonian, because there's no Hamiltonian. And then the standard, there are many options. The standard is the graph transform. And then here we do compute the manifold. We don't do changes of variables, but we look for the manifold. So the idea is very simple. So let me write the differential equation. So this is the central part. This is the hyperbolic part. So I decouple linearly. That's very easy, the linear change. That's degree 2 at least. This is what I'm writing here. This is degree 2 at least. And then this is the center manifold. That I don't know. I simply plug it on the differential equations. I manipulate. And I construct an algorithm that computes order by order the expansion of B. Okay, there's nothing especially. So here I've written the way of doing it. So you have to expand. And there's only one point in that kind of expansion, which is difficult. So there's nothing. Which is a comment. Well, that's the algorithm I've written here. So how it works. Which is I'm looking for the comment here. Okay. So one of the steps consists in doing these computations with power expansions. And here it appears a composition of power expansions. It appears here and here. So V is a power expansion, and G, it could be a power expansion, usually. I mean, if I work in the way I was planning, this is power expansion. I mean, composing power expansions is a very bad business. The amount of work is huge because you have to compose the full series on each monomial. So that's something that it's, I mean, theoretically you can do it because it has no cost in a theorem, but in a computer, that's not. So instead, we use another mechanism, which is recurrent expressions. And this is something I will discuss in the next lessons because I will use it in different places. Okay, I also put some references about this. And then the bibliography. I mean, that's the, let's say this is a very basic, reference list attached to what I was saying. So it's that. So I have this. This is also a book by Alex about invariant manifolds, which is very good. And then it's some papers of mine where I'm doing this and some books. Okay, so that's it. And I finish, I think, right on time, which I don't like to, to talk over time. So thank you.
Thank you very much. Very impressive summary of a huge subject. Very nice. So we are open to questions. If someone wants to ask question, can also put in the chat if can, or public is a little bit shy.
I have a question.
Please.
Angel, it's not clear for me if the procedure you presented build a unique transformation that leads you to the normal forms, or if it is not unique, how you can choose something or something in the middle in order to increase the convergence or something like that.
Yeah, well, you have many options and you choose one. The point is, let me go here. Yeah, here. Okay, that's I'm looking for here. So let me discuss it with G3. Okay, G3 we choose. So in principle, we choose it according to what we like. Okay, so then the first criterion is to arrange H3. So I want to suppress some monomials of H3, and this suppression is done when this thing is added. So this monomial gets cancelled, so it disappears here. That's how it goes. So the first criterion is to decide which monomials I want to make disappear. Okay, that's the first. So in principle, if you want to maximize the domain of convergence, what you have to do is to suppress the less possible number of monomials. Yeah,
I see.
So the more monomials you suppress, the smaller the range of convergence will be.
Okay.
Okay, so in principle, when I ask you, what do you want to suppress? So a first answer is everything. Why? Yes. Why? If I can suppress everything, why should I only uncouple? Right? I kill everything. But then the point is that if you do that, the domain of convergence of your expression, the domain of validity shrinks, and then you cannot study what happens if you go away.
Okay.
Yeah, so that's the price you pay to kill everything. So then, of course, you want to go, I don't know, as far as possible from the expansion. This means not to kill anything, which is also not an option because you want to kill something. So you have to decide which monomials you will kill, and then you have to try to kill the minimum number of them. There's not a unique way of uncoupling the manifold, right? There's not a unique way. So I've chosen one, and that's the one I'm presenting, but there are others.
Okay, thank you.
I don't know if I've answered the question.
Yeah.
Yes, I think so. Thank you, Maisa, for the good question also. Here we have something from the chat.
Oh.
So we
I
have...
should see the chat. If I stop sharing, I see the chat.
Yes. So can you read it or?
Slide 23, we can perform. I'll go back to the. So let me.
If you want that.
Okay. Yeah. Let me answer the question. So let me share again the formulas. I share a screen. That one, share. Okay, shared again, right? Yeah, the question is if I could transform this in action angle. Well, I could. And in some calculations, it is in fact done. But here it would be not a good idea. The point is that if I do this transformation in Q1 and P1, so I have to do it not only in H2, but in all of them. Because I mean, I will transform so that's the transformation I will have to apply. Okay, I'm doing this degree by degree, but I have to transform the whole thing. Yeah, so I have to transform. So here, if I go to action angle variables, remember in the action I will have a square root. So the square root is harmless for even powers because it disappears and you get, but if not, you get a square root, right? And then you have a square root, this property is not true because you don't have any longer, I mean, an homogeneous polynomial. So you enter, dangerous ground if you do that here. I wouldn't, yeah. I hope I have answered.
We say thanks.
Yeah.
Question?
Hi, Angel.
Hi, hey, Alex.
Hi, how are you?
Hi.
We are very far from here. So,
Hi,
so hi, Estefanel and all people.
Hi, Alex.
Perhaps you could mention something about this convergence of the expansions. I quote convergence. Maybe you mentioned something, but not all.
Yeah, I went too fast because, it's an interesting question. Sure. Which slide it was? That slide, right?
Mm-hmm.
So this is for L1 of the restrictivity problem. This is a computation up to degree 46, which is it's high. So these squares, those are the values of these. That's the root criterion for the convergence of the power expansion. Okay, so we take the power expansion, we apply the root convergence to the coefficients. Yeah. And this gives you the inverse of the rise of convergence. Those are the dots. Then the line is this function. So this is a fitting done using the last part with a bit of hand cooking in the fitting. Okay, so what you see, this is not a proof, this is simply a conjecture, that it seems that the radius of convergence, the inverse of the radius of convergence, behaves as a logarithm. So if this is true for all degrees, it means the radius of convergence will be 0 if you transform up to infinity. But that's a conjecture. Yeah, is that what you asked, Alex?
Alex? I suppose he was asking this.
Yeah, I suppose.
Sorry, I was talking, but Yes, but then even if these series are divergent, the divergence is very, very mild, no?
Yes.
So this is.
So I mean,
these asymptotic expansions are very useful, no? Because.
Oh yeah. This is if you decouple up to degree 46. I mean, to decouple up to degree 46 is a lot, huh? Well,
yes.
But I mean, for working with power expansions up to degree 46 is more beyond necessary. Let me know. Okay, so it is, and still the inverse of the radius of convergence. Look, that's the inverse of the radius of convergence. So you have a radius of well 0.9. Yeah. So it's, although this will reach, I mean, a logarithm will reach any value. So for reasonable expansions, it behaves as convergent. The reason for the good behavior is the lack, I mean, the absence of small divisors in the process.
Exactly.
With small divisors, you have a much worse behavior.
Thank you.
Yeah, thanks.
Some more questions? No?
Excuse me, Angel, would you mind going back to, I believe, slide 36, 35 or something? Just a question out of curiosity, really. I mean, regarding the fixed points, I guess you showed it, right?
That one?
Yes, this one. I mean, I was a bit lost here. I believe the explanation that, I mean, I should be thinking about being on Earth, looking at the sun. And
yes.
You know, but one thing that got me thinking was like this fixed point.
Okay, so
the set of fixed points actually. When you higher up the energy, the H, are they related to those Lagrangian points you showed it in the beginning, like L1 to L5? Are they related in some fashion?
No, this is neighborhood of L1.
Neighborhood of L1. Okay.
Yes, I mean here I didn't mention that. Maybe I should say I've rescaled distances such that the distance from L1 to Earth is 1.
Okay.
Okay, that's simply to avoid the very small numbers. Okay, I mean rescaling has also, I mean, some benefits about accuracy of expansions, but it's a small benefit. I haven't mentioned that. That's very technical.
Okay, right.
But I mean, this is the neighborhood of L1, so you don't reach. So you have to think that the Earth is if this 0.5. So let me go to higher order. So the Earth is here. Sorry, here.
Okay.
That's
the 0 at the origin, pretty much.
It is near -1. Yeah. And that's why it's difficult to go higher, because the radius of convergence is well, it stops because you have a singularity.
Okay, yeah, that makes sense. Okay. Just another question, like moving now forward, I believe slide 68 or something, 67, when you talk about, I believe, is the other kind of approach you could have. Sorry, I mean, I really didn't manage to get all the terms right. But yeah, the system at one back, 65, I believe, when you talk about when you define the center manifold as being y equal to some v of x.
Yeah, that's the center manifold.
I mean, just again, out of curiosity, like, could there be? How do we know that this is the equation for the center manifold? Isn't there any other like more difficult? Why aren't there any other more difficult relations?
Why? I mean, why it's y as a function of x?
Yes, exactly. Why it's not a mixed function of y and x equal to some constant, for example?
It's because of well, you have a fixed point, an equilibrium point, and then in that equilibrium point, we arrange the equations linearly. So we start at first degree because it's an equilibrium point. Okay. So, and we do a linear change. So we uncouple the elliptic from the hyperbolic.
Okay, that makes sense.
Okay, and because of this form, the manifold is so maybe I should do a drawing, but I mean, if I cut here, if I cut these two terms, if I cut to second order, then the center manifold is y0. You agree?
Y0, I believe so.
Y equal to 0. That's the center.
Yeah, sure.
Okay, they are decoupled, so you kill. So you suppress the hyperbolic behavior of choosing y equal to 0.
Okay, Makes sense.
That disappears, and that's the behavior inside.
Okay, all right.
Yeah. So if you do, maybe I don't know if I should use, I plan to make a drawing. So it's so let me try to make a drawing. So I prepare the table in case of, I mean, my tablet in case of need. So let me see if it works. So share. Here. Now you're supposed to see my tablet.
Yes, you can see it.
Yes.
Yes. Okay, so this is X, this is Y. So in principle, if we cut to degree 2, Y equals 0 is the center manifold. Okay, so we do something flat here. Yeah, this X is 4D and this Y is 2D.
Right.
So, well, if we perturb this, we have the second degree terms, the perturbation of this becomes maybe something like that, I don't know. Or maybe something like this. I'm not very good at drawing and even less in a tablet, but
I can get it.
yeah, you understand. I mean, this is a 4D manifold in the 6D ambient space. And this is because, I mean, this manifold, because when for the second degree it has this form, here you can write it this way.
Yeah, now it all makes sense. Okay, now I see it.
Yeah. So in fact, V will start with second degree.
Okay.
Because the first degree is 0. So the first degree is 0. So we will start with second degree.
Okay, that makes sense. Right. Thanks a lot.
Thanks.
Great. So students are getting not shy to ask it. Very good.
So in fact, let me say something. I mean, simply, I mean, today was the most probably technical class because I'm using the Hamiltonian structure, which is a little monster that I'm hiding behind the door. But it's, I mean, the amount of mathematics behind this is, I mean, I'm hiding a lot of things. So it's difficult to follow all the details. So in the next classes, there's a mathematical background, but maybe it's not as big as this one. So I think it would be simpler.
Okay, so very good. Excellent. So we have even Claudio that got here.
Oh.
Okay, so more questions? No? Well, it's getting late there in Europe. It's past 8, you know? It's what time is it?
Yeah, it's yes.
8:30.
8:16. Yeah.
So thank you for making these extra hours for us.
No, that's fine.
It's very nice to see these beautiful things. And so we'll, if you send me the slides, whenever I can send to the people there to receive the material, try to register. It's easy to send it to you if I have your mailing list. Okay.
Maybe it would also be good to share the page of Andy, because he mentioned that there was the program there in his page.
Yes, Angel, can you?
Yeah, it's
post
let me
it?
do it. Sorry.
Thank you very much.
So it's
Gladstone already share here on the chat. Thank you, Gladstone.
yeah, that's my webpage. Can you see it?
Yes.
Yes.
So I have this, you know, this software. So I have a few things, not too many. And the one I was talking is that one. That's very old, but it does is that part. So there's the software. so you can play with it or.
So let me stop.